Okay, so the plan for today is to finish this one last problem in 2.6, limits at infinity, um, and work our way through 2.7. And as I mentioned, we'll cover 2.8 and start chapter 3 next week. The quote of the day, or kind of idea of the day, is a couple related ideas. Um, One is make strategic use of the learning curve. There's a couple related ideas that people kind of call the learning curve, but in some sense, kind of as you're a beginner in a field, uh, progress seems kind of difficult, but you're actually making a lot of progress pretty quickly. So your time spent near the beginning of your learning in a certain field gets you quite a lot of yield typically. That same time spend, you have diminishing marginal returns over time that same time spend when you're saying intermediate gets you a lower level of yield. And when you're an expert, that time spent gets you a very small marginal yield. So if you want to be the best in the world at some certain thing, you pretty much have to devote your entire life, all of your time and energy, cognition, and all of that to that thing to become like the world authority on whatever that thing is. But you might be able to leverage this early part of the learning curve and become kind of a jack of all trades, right? I mean, a lot of times people that gets kind of a bad rap, jack of all trades, master of none, um, but a lot of times it's very useful to be able to have broad knowledge across a lot of different fields at kind of a maybe advanced beginner level to at the very least know when you need to seek expert help in those fields and then be able to go deep in a couple of specific areas. So one example might be, if you're looking at going into, say, finance, um, having a little bit of computer programming skills or a little bit of data analytics skills is going to be super helpful, even if that doesn't apply directly to your job. But having a little bit more breadth of knowledge can either make you stand out from other candidates for a job or maybe contribute to your ability to do that job. And then kind of related to this idea, this is kind of one of my mental models of the the types of knowledge that we might be interested in acquiring. I kind of divide knowledge into four quadrants, things that I'm interested in learning. One of them has to do with the time constant, so to speak. So how quickly does the utility of that knowledge decay over time? So we have very dynamic types of systems versus static ones. So for instance, uh, if you learn a mathematical theorem, if you learn the definition of a derivative, it's going to be the same definition. It's going to have the same utility a month or a year or 10 years from now. Versus if the example I always use is if you were watching, say, the football game this past weekend, well, you can talk about some interesting play or what happened with your buddies around the water cooler this week, but probably 3 or 4 weeks out, nobody's going to be really interested in that anymore. So that time spent to acquire that knowledge of what happened in that game and so on, that goes to zero pretty quickly. That's not saying you should never spend time learning that stuff. That can be useful, um, but it's something to just keep in mind. And related to that is trivial versus foundational. In other words, if I learn this piece of knowledge, is it just kind of an isolated island of knowledge that I can't really connect to anything that I really know already, or that doesn't give me any additional perspective on the stuff I already know, and that I can't really build off of and connect it to other things in the future? Or is it more foundational? So again, we're going to learn about definition of derivative, and that will lead into some applications of derivatives and optimization and linear approximations, and we're going to build off of that, right? Math tends to be kind of in this static foundational category down here. And that's kind of my bias. I tend to prefer being in this quadrant when I learn something. Uh, I feel like if I learn something, I don't want to have to relearn it over and over and over again as things change. And I want to learn something that I can connect to other pieces of knowledge and build off of. But that's not to say that other quadrants aren't useful. And for two examples, um, for fields that have more of this kind of dynamic trivial knowledge, things like IT, for instance. I mean, IT support, you come up with some update to some system, and these folks have to go in and relearn all of the stuff that they learned about the last version of the system. They have to relearn a bunch of things because the system was updated and things work a little differently. Um, so that knowledge they used to have has diminished and they need to rebuild it. Or like accounting, right? Something changes in the tax code and things change every year and they have to constantly keep on top of these things. Again, that's not to say that this is a useless quadrant or anything like that. I mean, I certainly am very happy that there are folks who enjoy that process. Some folks really enjoy keeping up with all of the changes and, keeping up to date with all of this and constantly updating their knowledge. It's not my cup of tea, but it's something maybe just to think about, what quadrant of knowledge do you like to be in? Um, where do you feel comfortable? And, does that kind of mesh um, with your career plan or the courses you're taking? So, uh, just a couple little thoughts for today. Not an official quote, but maybe an idea, maybe some things to think about. Okay, so again, today's plan, finish this one problem in 2.6 and then move on to 2.7. So we left this last problem as an exercise from 2.6. Here we have limit as x goes to infinity of 3x minus x cubed. And we see that this is kind of an infinity minus infinity type limit. If I plug in a large positive number, I get large positive minus large positive. That's like infinity minus infinity. And again, that's kind of a tug of war that can end up as negative infinity or positive infinity or somewhere in between. This is an indeterminate form. And we have an indeterminate form. One of the things we look to do is to do some algebraic either simplification or manipulation to help us figure out what's going on. And one thing I notice I can do here is maybe factor out an x. If I factor out an x, I get limit x goes to infinity of x times 3 minus x squared. Now, if x is going to infinity, I can certainly assume that x is bigger than 0 without any real problems. From the definition of my limit as x goes to infinity, I'm looking at values of x that are above some certain number, so I can certainly restrict my point of view to only positive numbers, not a problem there. And in this regime, when x is bigger than 0, of course, my first factor is positive. And my second factor, 3 minus x squared, well, let's, instead of making x bigger than 0, let's make it bigger than something even a little bigger. Let's say, x bigger than 3. I guess we could go with square root of 3, but I don't really have enough room to write square root of 3, so we'll make x bigger than 3. When x is bigger than 3, again, there's certainly no problem doing that because x is going to infinity, so I can restrict it to be as large a number as I like. I notice that 3 minus x squared is always going to be negative. As I plug in a bigger and bigger value for x, I'm going to get a bigger and bigger positive number times a bigger and bigger negative number. I know this result is always going to be negative. Again, for sufficiently large x's, it'll always be negative, and it'll be getting bigger in magnitude. This limit is clearly negative infinity. So any questions on limits at infinity and horizontal asymptotes, these limits where x goes to plus or minus infinity? Okay, so let's move on to section 2.7 then. So 2.7 and 2.8 introduce the idea of a derivative, where we're going to really kind of spend much of the rest of our time in this course until maybe the last few weeks of the course when we talk about integration. But differentiation, derivatives, properties related to it, applications of it, and so on is where we're gonna really live for the next probably month and a half, 2 months or so. Okay, so we have a definition of a tangent line. The line tangent to the graph of y equals f of x at x equals a, or just kind of in short, the tangent line to f at a, something like that. That's maybe not quite a precise way to say it, but that's the way we'd usually say it, the tangent line to f at a. But if we wanted to be more precise, it's really the line that's tangent to the graph of y equals f of x at x equals a is the following. Well, it's a line, of course. I can define a line with two criteria, one of which it has to go through the point of consideration, a comma f of a. So I have a point. If I have a slope, point slope form gives me uh, the equation of that line that lays out a unique line. So I have a line through a point a f of a with the following slope, m equals limit h goes to 0 f of a plus h minus f of a over h, which is equivalent to limit as x goes to a of f of x minus f of a over x minus a. And this is provided the limit exists. This limit may not exist. We know that limits can exist and be real numbers, or the limit could not exist, or I suppose the limit could exist and be an infinite number. So maybe we would want to append here and is finite. Although if we had an infinite limit here, we might be able to kind of make some sense of what that means. And this is kind of reminiscent of what we did pretty early on in chapter 2. We had a point of interest A. We had a deviation H. So a second point, A plus H. We drew a secant line through those 2 points. And then we asked, what's the slope of the secant line? The slope was the difference quotient for that given H. And I guess we could call it like F at A or something like that. And we asked what happened to this difference quotient as H gets smaller and smaller. And we looked at that very empirically. And that difference quotient was F at A plus H minus F at A, the rise, over the run, A plus H minus A, which is just H. That was one perspective. We had another perspective as well. Again, point of interest A, a second point on the curve X, comma F of X, secant line connecting them. And the slope of that secant line was the rise, f of x minus f of a over the run, x minus a. And then we looked at what happened as x got closer and closer to a. X could get closer to a from above or below, same with h. We're just drawing it this way for convenience, but we could have also picked a second point to the left of a for both of these, and that would have been fine. So all that we've really done is formalized what we did at the beginning of chapter 2, but under this definition of limit. An important thing to note is that if I am tempted to do my plug-in operation, if I just plug in h equals 0, well, if I plug in h equals 0 geometrically, what that means is I'm just picking the same point twice. I don't really have two distinct points to give me a line. And algebraically, what that means is I get 0 over 0. I get an indeterminate form. So although we were really tempted to do the plug-in thing all the time, we said we have to be careful not to do that. And it wasn't just this kind of, strange cases that I pulled out of nowhere that broke. We see that that's really inherent in the definition of tangent lines, and we'll see later in the definition of the derivative that we always get this kind of an indeterminate form, and therefore we can't just do the plug-in property. We're always going to end up, when we're evaluating such limits that relate to tangent lines or derivatives, we're going to end up with a situation where We can't just plug in. We have to at least do a little bit of simplification or reasoning first to get rid of the indeterminacy. We have a second definition as well, very similar looking definition, just a different way to discuss the idea. The tangent line idea is a very geometric kind of idea. And we have this definition that is kind of the more algebraic side of things. The derivative, or the instantaneous rate of change of a function f at x equals a, is denoted like this, where we have kind of f with like an apostrophe next to it of a. We would verbalize this as f prime of a. We use the word prime to signify that like little apostrophe there. And we define f prime of a to be the similar limit as above. The limit of the difference quotient, limit h goes to 0, f of a plus h minus f of a over h, which is equivalent to limit as x goes to a, f of x minus f of a all over x minus a. And as before, provided this limit exists. So the kind of meat and potatoes of the two definitions, this limit, these are the same limits between the two definitions, but just the context is a little different. This is the kind of geometric interpretation, the slope of the line tangent to the graph. And this is the more algebraic interpretation. That's the derivative. It's some characteristic of this function f at that point a. Okay, so let's take a look at a specific function at a specific point and see if we can figure out what's going on here. So if we have f of x equals x squared, let's try to find f prime of 3. And as an aside, kind of sometimes we'll use the h definition, sometimes we'll use the x definition. Sometimes there is kind of a good reason for this. Most of the time it's just kind of I switch back and forth because I want to, demonstrate both of them. As you're going through and maybe rewriting your notes, not a bad idea to say, like, for this first one, we'll use the h definition, go through and use the x minus a definition, and see if you get the same result, just as practice. Go through and use the other definition and try to get the same result. I don't think anything that I've picked here will be super difficult to make that work out, one way versus the other. And it is really just kind of a change of variables, right, to get from one to the other. So it's not really fundamentally different definitions or anything like that. It's just whether I think of the second point as being h units away from a, or whether I think of the second point independently as having x coordinate x. Okay, so f prime of 3, well, what is that? By definition, that is the limit as h goes to 0. In the h definition, h always goes to 0. In the x minus a definition, x goes to a. So x might go to 2 in one example, and x goes to 3 in this example, and x goes to 5 in another example. But in the h definition, h always goes to 0. The deviation from the point of interest always goes to 0 in our limit. And I need f of a plus h. Well, that's f of 3 plus h minus f of a minus f of 3 over h. And here I want to be careful about my functions, my function evaluations, my all of my algebra, arithmetic, all of that kind of stuff. No taking any shortcuts here. So f of 3 plus h, that means I get 3 plus h all squared, which is not 9 plus h squared. We have a cross term there. Minus f of 3 is 9 over h. Again, some folks like really want to make this like f of 3 plus f of h or something, or they really want to just plug in h equals 0, or they plug in h equals 0 and see the divided by 0 in the bottom and say, oh, this doesn't exist. This limit doesn't exist because we have a 0 on the bottom, but we also have a 0 on the top. That makes it an indeterminate form. So we have to be careful with the details here. no sloppy algebra, no sloppy logic. You know, taking it step by step and being careful is probably the best way to avoid that. 3 plus h all squared is 9 plus 6h plus h squared minus 9 over h. I see my 9 minus 9 cancels. And then I'm left with 6h plus h squared all divided by h. I can divide out the h and I get 6 plus h. Oops. And now I have limit h goes to 0, 6 plus h. Well, now I just have a polynomial. I know polynomials are continuous functions. I know I can now do the plug-in property. Doing the plug-in property, I plug in h equals 0. This just gives me 6. So f prime of 3 equals 6. Or the instantaneous rate of change of x squared at x equals 3 is 6. Or the slope of the line tangent to the graph of y equals x squared at x equals 3 is 6. Whatever interpretation is most suitable or meaningful in whatever scenario you're in is the one that you can use. Kind of a little side note, a little, I like to throw these in every once in a while, these kind of gut feeling things. Like how should something work? When I think of h going to 0, I think of h being small. And as kind of like, again, this is very hand wavy, this is a very gut feeling kind of thing, but sometimes building up this intuition alongside the precise algebra skills, the intuition can sometimes lead you down the right path, right? You want the algebra skills to actually take you down that path, but you might say, should I go this way or that way? Maybe the intuition gives you an idea. As kind of a general calculus idea, this h, this deviation, we think of as being small. Limit h goes to 0, we think of h being small. And the square of a small number, we think of as being like a 0. So in other words, this h squared does not come into play. I mean, it is there algebraically. We have to go through the steps and make it work out. But this term that's the h term does come into play, right? We see this 6 pop up in the answer, but the h squared just kind of like fizzles out, right? It turns into this h, which turns into a 0. So if I have higher than first power of small numbers, those essentially become 0. This is actually a really important idea in things like linear approximation and so on. So this is an idea that kind of carries through a lot of calculus. And even, this idea carries through much more broadly into even other fields that use calculus quite a bit. That I can, in some sense, kind of ignore small squared or small cubed terms, but I probably don't want to ignore small to the first power terms. Now, again, I don't want to just go crossing something out just because it has a square on it. I need to do the algebra to make that happen. But that gives me a little bit of an idea of what I'm shooting for, what path I might want to go down. So the stuff I wrote in red is gut feeling kind of stuff. It's intuition kind of stuff. It's not the precise algebra. The precise algebra is what I did in black. But in a more complicated problem, if I was saying, where am I trying to go to make this work out? This might give me some intuition, some idea of where I might want to go. Okay, let's look at the function f of x equals root 1 minus 2x. And here we want to find f prime of a, where a is in the domain of f without 1/2. Well, what's the domain of f? It's when 1 minus 2x is bigger than or equal to 0, or that's whenever x is less than or equal to 1/2. Here we're taking away 1/2, so we're looking at a strictly less than 1/2. And we might see algebraically why we need to do this, but just following our nose algebraically, we end up with this result. We see that a has to be less than 1/2. Why can't a be equal to 1/2? Maybe we'll address that after we see the algebraic result. So let's find f prime of a for a strictly less than 1/2. All right, so f prime of a, here we'll use the limit x goes to a definition. And what do I have? I have limit x goes to a, f of x minus f of a all over x minus a. Or f of x minus f of a. Why did I use the x go to a definition here? Well, because I'd rather not have square root of 1 minus 2 times a plus h. That's just a little much under 1 square root. It's not, it's not that I couldn't handle that. It's just that it's a little more cumbersome to work with. And then I have divided by x minus a. Now I look at this and I think, okay, at this point, I know this is like a derivative, but it's also just a limit problem at this point. Have I seen similar limit problems before? Well, yeah, I've seen similar limit problems where I had an indeterminate form, I had square roots in it, and kind of the problem here is if I just tried to plug in x equals a, I get 0 on the top and 0 on the bottom. That kind of suggests that maybe I should do some algebraic work and try to get something to cancel. I'm trying to make the top have an x minus a somewhere that I can cancel with the bottom x minus a. And the way I've done it in the past for these kinds of problems with square roots is I typically would multiply by the conjugate. So root 1 minus 2x plus root 1 minus 2a, both on the top and the bottom. Now on the bottom, I have x minus a, and what I multiplied by. Note now that if on the bottom I plug in x equals a, I get in this factor root 1 minus 2a plus root 1 minus 2a. I just get 2 root of 1 minus 2a. So it doesn't zero out anymore because I'm not subtracting the same thing from itself. I'm adding the same thing to itself. In the numerator, my firsts multiply together and give me 1 minus 2x. My outers give me the same thing as my inners, except opposite signs. So when I add those together, I get 0. And then I get minus from my lasts, 1 minus 2a. Let me be careful with that minus sign there, make sure it distributes properly. And I see I have 1 minus 1, my constants go away on top. And I have, oh, can't forget my limit. On my top, I guess I can pull out a -2. Then I have an x. And if I pull out this -2, I have a minus a. I think that's everything from the top. And just the same stuff on the bottom. Now, nicely enough, my x minus a's divide out. And now I have a limit where I can go through my limit properties, limit of the quotients, the quotient of the limits. And the bottom, this limit of the sums, the sum of the limits. Limits can come inside roots, which are just powers, so long as everything works out okay there. And if I do that, I see that ultimately I can just plug x equals a all the way in here. So I get -2 over, and then I get root 1 minus 2a plus root 1 minus 2a. That's 2 root 1 minus 2a, or this ends up being just -1 over root 1 minus 2a. So algebraically, f of 1/2 exists just fine. It's the square root of 0, which is just 0. But f prime of 1/2 would be like -1 over 0. So 1/2 can't plug into f prime. That was the reason we had to be careful with restricting our domain just a little bit further. So algebraically, that's clear, just kind of following our nose through the algebra, seeing what we got at the end. And the square root, instead of being in the top, we're having a 0 is no problem. It ends up in the bottom, we're having a 0 is a problem. And that means we had to restrict our domain a little further. What's going on geometrically? Well, our square root looks like this. If my point of interest is, say, here, I have a nice, well-defined tangent line that makes sense. If it's here, I have a nice, well-defined tangent line, right? I can make secant lines that approach it and all of that. If my point of interest is right here at 1/2 comma 0, I mean, I guess I can have like a bunch of tangent lines, right? That would just touch at just that one point, at least locally. So that's the problem here. This is kind of like having a corner, except, the other half just isn't there. So that's really what's happening geometrically, is that I don't have a clear sense of a unique tangent line at this point. Kind of any line going through that point, uh, could be a tangent line in some sense. And I suppose we could go a little bit deeper with that interpretation, but I think I'm going to leave it there. So we could actually think about maybe going a little bit deeper. Well, what if I took the limit of the slopes of my tangent lines as a gets closer to 1/2? That might be an interesting thing to kind of think about, but I think we're going to leave it there with this problem. Questions so far?
So wait, what exactly is it again then that F prime is telling us about?
Yeah. So f prime of a, on one hand, we've computed it. So for any value of a that is strictly less than 1/2, f prime of a is whatever I get out by plugging a into here. So if a was 0, I would get f prime of a is -1. So that's kind of algebraically. We see that 1/2 is in the domain of f itself, but we see that 1/2 is not in the domain of f prime because that would put a 0 in the denominator. So algebraically, we see why our derivative is only good for a strictly less than 1/2, not for a equals 1/2. Geometrically, we see that because going all the way back to the beginning of chapter 2, we were talking about things like finding the slope of a tangent line by constructing secant lines that become better and better and better approximations to the tangent line. But the problem down here is that a tangent line is a line that touches the function at exactly one point. And I could make, say, this line that touches at one point, or this line, or this horizontal line, I could make lots of lines that just touch the function locally anyway. Might touch it over here or something at another point, but we're speaking locally.
Okay, so that thing's just like rotating in space.
Exactly. It's a little bit like if I had a car tire or something, I gave you a 2x4 and I said wiggle the 2x4 until it touches at this point on the tire, you could do that and the 2x4 would be in a certain spot. But if I gave you like a knife edge and told you to do the same thing, you could kind of wiggle the 2x4 a whole bunch and still satisfy that criterion of just touching in that one spot. And that's kind of what's going on here. Is you can almost rotate that line about this point, and pretty much any way you rotate it, it's only going to cut the function, or it's only going to touch the function 1 point locally. It's not going to, cut it arbitrarily close.
Okay, thank
Where,
you.
yeah, sure. Yeah, that's good question. So, when jumping ahead a little bit here, this is kind of using section 2.8 terminology, but the domain of the derivative could be different than the domain of the function. So that's something to just be aware of. Okay, so next example, suppose the position of a particle on a line, we could call that its displacement, is given by s of t equals t squared minus 8t plus 18. And we want to find v of 4, the instantaneous velocity of the particle at time t equals 4. So instantaneous velocity is the instantaneous rate of change of position. And so we're leaning on this derivative. This is just the derivative. So velocity is the derivative of position, or v at 4, the instantaneous velocity at time 4, is just s prime of 4, the derivative of the position or the displacement at time 4. And this is limit, let's say limit t goes to 4 of, what do we need? S of t minus s of 4 over t minus 4. So s of t is t squared minus 8t plus 18. So that all came from here. And then minus s of 4. Let's just figure out what s of 4 is. Well, that's 4 squared is 16 minus 32 plus 18. So 16 and 18 is 34 minus 32 is 2. Simplifying a little bit, t squared minus 8t plus 18 minus 2 is plus 16. And then over t minus 4. This again results in a 0 over 0. We could see that by plugging in t equals 4, or just by kind of understanding that these derivatives always end up giving us a 0 over 0. So I'm looking to divide out a t minus 4 from the numerator. And I see indeed in the numerator I have t minus 4 all squared over t minus 4 in the denominator. I can divide one of them out. And now I just have a polynomial. Now I can do the plug-in property, no problem. I have the either theorem under continuity or theorem under a previous section that says I can plug in here. 4 minus 4 is 0. The instantaneous velocity here is 0. So if I think of my position function as being whatever it is like this, my instantaneous velocity, my instantaneous rate of change is also related to the slope of the tangent line. This is also where the tangent line is horizontal, has slope 0. This kind of represents, like if I'm throwing a ball in the air, the apex of that arc of the ball, where the ball isn't really going up or down anymore. And here I'm thinking of, physically speaking, I'm throwing the ball straight up and it's coming straight down. Just over time, how is the height of the ball changing? It's starts off at height 18, gets higher, and then gets lower over time. But it's just moving in one dimension, going up, and then coming straight back down. But it's going up for a while on time 0 to 4, and then time 4 to infinity, it's falling down. And right at time 4, it has 0 velocity. It has reached the top. It's kind of on the transition between going up and going down. It's kind of, hovering still right there for just that one instant. It has 0 velocity. Any questions so far? Okay, so let's look at an example here. And um, okay, so let's look at this example. I have something to say about it, but I will hold off saying that for just a minute. So if I take a look at this statement here, f prime of a equals limit as h goes to 0 of 1 plus h to the 10th minus 1 over h. Let me consider what f of x and what function and what input or point of interest would say, let's say something like naturally give rise to this limit interpretation of f prime of a. Now, I mean, you know, that's maybe, you might say this is an ill-posed problem because what does it mean to naturally give rise to that? But I think we kind of understand what I'm asking here. So this isn't a super precise and super accurate question, but I think we kind of understand what's being asked. What function f of x and what input a would naturally lead me to this limit? Well, I know that f prime of a is limit h goes to 0, f of a plus h minus f of a over h. So I'm kind of looking at 1 plus h to the 10 as something like f of a plus h, and I'm looking at, say, 1 maybe as being f of a. Well, if I pick f of x equals 1 plus x to the 10 power, and if I pick a equals, if I pick a equals, uh, brain fart moment, let me erase that. If I pick f of x equals x to the 10th power, and if I pick a equals 1, then f of a plus h would be f of 1 plus h is 1 plus h to the 10th, and f of a, or f of 1, would be 1 to the 10th, or 1. And that would work out here. Everything would match up. Now, something we might be interested in asking is, okay, so in the most technical sense, this limit is just a number. It's a number, let's just say it's a number like 3. It's not 3, but let's just pretend it is. Well, I mean, you could find tons of f's and tons of a's that give you a derivative of 3. So, technically speaking, you know, any f and any a that give you a result of 3 could be changed into this limit. You could say that they're equal, but I don't think, there are many that would naturally give rise to a limit like this. But what if I came up with a slightly different f? Let me remove these check marks. Maybe my f of a plus h kind of, instead of looking like 1 plus h to the 10th, if it looked like 1 plus h to the 10th minus 4. And my f of a, instead of looking like 1, if it looked like 1 minus 4. Well, then what would f of a plus h minus f of a be? Well, I see that actually this minus 4 gets subtracted off between the two. If I have a constant added to the end of my function, it just kind of goes away in the numerator. Let's rewind a little bit. And up here, let me edit this just a little bit. Instead of writing minus 2, let me write minus, and s of 4 was all of this, right? 16 minus 32 plus 18. Well, hey, there's this 18. They just go away. This extra little constant bit there, it actually didn't have any effect on the derivative at all. What effect does that have on the function? If this was a plus 20 instead of 18 or a minus 5 instead of 18, all that would do is shift the entire function up or shift the entire function down. It wouldn't change the slope of the tangent line at 4 because it's just moving the whole function up or down. It's not changing any of the angles. It's not shifting things left or right or anything like that. So in fact, when I'm looking at the derivative, I actually don't care about constant terms. My derivative kind of, in a sense, throws away any information about constant terms. It does keep information about, you know, non-constant terms. That's important in the computation of the derivative. But if I knew that this is what my derivative looked like, and again, what are some functions that would naturally lead to such a derivative? I could reasonably say anything that looks like 1 plus h to the 10th plus really any constant. Then f of a would be 1 plus constant, and their difference, the constants would just subtract off. So actually, kind of any constant added to or subtracted from a function doesn't really change the derivative at all. And in fact, we saw earlier that, if I just had f of x equals constant function, the tangent line is always horizontal, the derivative is always 0 for that function. So that kind of makes sense, right? If it was just the constant function I was looking at, its derivative is always 0. So kind of adding on a constant seems to have like 0 impact on my derivative. And again, thinking more geometrically, if I add on a constant that just shifts the whole graph up or down, that doesn't change anything about tangent lines or slopes or anything like that. It just moves the whole thing up or down. It changes what specific point I go through that I'm interested in, but it doesn't change the derivative information, the slope of the tangent line or instantaneous rate of change or whatever. Right? If I was throwing a ball straight up, according to this, you might recognize this as kind of like under the influence of gravity in some units and with some initial velocity, the ball is still going to stop going up and start coming down after 4 seconds, whether I'm standing on the top of a skyscraper or standing 10 feet underground or standing right at the surface, whether I'm plus 18 or minus 10 or plus 0. The ball is still going to stop at time 4 and start going down. So I think this is also a pretty important idea going throughout calculus, that derivatives kind of throw away any information about constants added on. And algebraically, that happens through the subtraction here, that we just end up getting rid of these constants. And geometrically, I think I've explained a couple of different ways to think about that interpretation. any function like this with a equals 1, or I should say any function like this plus c with a equals 1 uh, would probably be a sensible answer to this question. Again, like, could you argue that there are crazy functions and crazy choices for a that would technically satisfy the question I asked here? Maybe, but there are some pretty reasonable ones that would naturally lead to such a limit definition. Okay, what about this one? F prime of a is limit h goes to 0 cosine of pi plus h plus 1 all over h. Well, I'm pretty clearly looking for a function that looks like something like this. So I'm thinking that f of a plus h is cos pi plus h. This kind of makes me think that a equals pi and f of x equals cos x. With these choices, f of a plus h is indeed cos of pi plus h. Does that mesh with this second part here? Is f of a, well, we would have minus a negative 1. Is f of a negative 1? Cos of pi is negative 1, so I feel good about that choice. Could I have picked cos of x plus 3 or cos of x minus 5? Sure. So I could actually pick cos of x plus c for any real number constant, and that would still naturally lead to the same limit definition. Now, I might look at a problem like this and think, well, wait, f prime of a is limit h goes to 0 of, but this is just the ratio of two things. I might be like really tempted here to do something like sine pi plus sine h, but sine is nonlinear. We can't break it up like that, so we don't want to go doing something like that. We have to be a little more creative. Any thoughts on what might have happened here?
Isn't sine of pi 0?
Yeah, exactly. Limit h goes to 0 of sine pi plus h minus 0 over h. And now it looks a little more familiar. F of x equals sine x. And let's throw in a plus c for good measure. And a equals pi. F of x plus h is going to look like, I'm sorry, f of a plus h is going to look like sine of pi plus h. And f of pi is going to be, if we pick c to be 0, it's going to be sine of pi, which is 0. If c was non-zero, we're going to get that constant canceling out. So these can be a little bit tricky. Or if I have an example like number 4 down here, f prime of a is limit t goes to 1 of t to the fourth plus t minus 2 over p minus 1. There's kind of a lot going on here. Let me first check and make sure it's an indeterminate form. If it's not, then I think something's gone wrong. But I get 1 plus 1 is 2 minus 2 is 0 over 1 minus 1 is 0. So I get 0 over 0. I know that my definition of derivative should always give me an indeterminate form, and that did happen here. So, well, nicely enough, I'm not in the h goes to 0 format of the definition. I'm in the t goes to a or x goes to a. So I know right away that a is 1, just from the structure of the limit. I also know that from the denominator here, that t minus 1 is the t minus a in the denominator. So then what's f of t? Well, I suppose it could be t to the fourth plus t. And then f of 1 would be 2. And that would work. It also could be t to the fourth plus t minus 2 if I wanted. F of 1 would then be 0. That would work as well, right? It could actually be t to the fourth plus t plus whatever constant I want. And then f of 1 will be what? 2 plus that constant. The constant is going to go away, and I get t to the fourth plus t minus 2. Everything works out. So some big takeaways here. Number one, again, uh, we got to play ball a little bit here. This is technically not a well-posed problem, but some big takeaways are that whatever function we come up with that we're looking at, if we add a constant to it, its derivative is going to look exactly the same. The calculation of the limit, the derivative, all the information about the derivative is going to be exactly the same for any constant added to a function. Also, we can kind of reverse engineer these a little bit by understanding where all the components fit together. And also, if we look at a limit and it turns out to not be in a determinate form, then it's not at least kind of the initial definition of a derivative. Now, again, we have seen, like, could I technically say that, s prime of 4 equals this limit? Well, sure. I mean, it's equal to that limit because it's equal to all of these, but it's not kind of the natural first definition of the limit. That initial definition of the limit is always going to be in a determinate form. And I really want to hammer this because I see so many students that just look at this and they say, oh, plug h equals 0 in. This is something over 0. It has an over 0 in it, does not exist. But then, like, if you're getting limit does not exist for like every problem in an entire homework where you're supposed to be computing a bunch of derivatives, I mean, just kind of like strategically, something should pop out at you and say, okay, wait, I think something's going wrong here. And the mistake is here that we're getting 0 over 0. This does not immediately imply that this limit doesn't exist. If we were getting something like 3 over 0, we would think that either limit doesn't exist or that it's plus or minus infinity, but this is an indeterminate form. And we want to do some algebra to try to divide out the thing that's giving us the 0 on the top and bottom. In a polynomial, that's usually pretty easy to do. We can just, subtract off, or we can just factor out a factor of h from the top and then divide it out. Or if we had a polynomial like down here, we can factor out a factor of t minus 1, if I can select it. Factor out a factor of t minus 1 from the top and then divide it out. In something like this, and that's not going to be really so doable. So evaluating these limits, don't try to evaluate these limits. They're going to be actually quite difficult to evaluate. We're going to have to take really a completely different point of view for, say, limits 2 and 3. Limit 1, you could in theory do. It's going to be super messy though. You would have to multiply this out. You would get 11 terms and then the minus 1. The ones would cancel. You could factor out an h and divide, but you would get a super messy thing. This one actually wouldn't be bad. If you want to do this one for practice, it's not bad. But the other three, 1 through 3, these would be pretty terrible limits to try to approach just like with kind of the sledgehammer method like we were up here, just cranking out the limit. When we get to chapter 3, we'll see some derivative properties that will make doing this derivative really easy, actually. Some of those derivative properties, and then we'll work through a more geometric argument for what limits like these might end up being. Are there any questions on anything from today? All right, so as I said, I'm kind of feeling under the weather today, so I think I'm going to end it a little bit early, but I think we did get through some pretty good information on section 2.7 today. We'll pick up next week 2.8. 2.8 is going to actually feel very similar to 2.7, just kind of a different philosophical perspective, but a lot of the algebra and the mathematical work will feel quite similar in 2.8 versus 2.7. So this being such a big idea, I actually don't feel too bad about splitting 2.7 and 2.8 up and seeing it on 2 consecutive days and getting kind of another quick review of some of this material. And then, of course, we'll start chapter 3 next week, where we'll move from the definition to looking at some properties and things, kind of like we did with limits, right? Once we had some properties, we could get rolling with limits a lot more easily than doing all this crazy, like plugging into the calculator 1,000 times kind of deal. Same thing will happen here. These working through these limit definitions is a bit tedious, but it's important to do a couple of times to understand what the foundations of the derivative are. But once we move into chapter 3, we'll be looking at properties of derivatives that will help us compute things more efficiently and compute more derivatives that wouldn't really be feasible to do with the limit definition.